So it's the last week of school. We're reviewing one more thing today and then possibly one more thing on Friday, and then I think we're going to call it. So today we're going to review division. We're going to review two different types, long and synthetic. Long division was a skill you knew when you came to me. Synthetic division was something that we used so much when we studied matrices, which is in fact something we've already studied and reviewed. So let's go ahead and talk about division. Let's keep it quick and be on our way. You should have notes that look like my document. They are notes in the sense of the word that you're looking at the same document that I have. There's not really a lot you need to fill in on these because this lesson could get really lengthy, and I don't want that for you or for me. So with that in mind, here we go. So long division is a way in which to break down a numerator, a value, in this case a polynomial, into its factors. And sometimes long division produces factors. Sometimes it produces some kind of a, I'm going to use the phrase partial factor because there's a remainder. And if there's a remainder, then, well, we've done that numerically, but we can also do that with a polynomial as well. So let's go ahead and review first the idea that division using factoring is still a way to do this, right? We don't want to minimize the fact that factoring are great at simplifying rational polynomials. And that's what we have here in this first example. However, long division works really well also, and it works in situations where factoring might not always be our best option. Now, I've taken the same exact problem and taken the numerator and put it on the inside of our division symbol. And we've taken the denominator and put it on the outside of our division symbol. And now we're simply going to divide. Something to keep in mind when doing long division, the size isn't a great phrase, but I'm going to go ahead and use that anyway. Think of the size of the divisor, right? This is the denominator, so it's the thing that we're dividing. We're going to take this thing and we're going to imagine layering it kind of on top of the beginning of the polynomial. And here's what that means to me. The end of my, gosh, how do I draw this? The end of it comes through the 4x, and that's where my first value is going to go. So that's how I determine kind of how big of a space to skip, shouldn't use x there, and where my first value goes. And it doesn't have to be a numeric value, it just has to be some sort of value. But that's how I'm going to decide where all of this stuff goes. So knowing that it goes in that box, and knowing that this guy over here is what I'm dividing in, I'm looking for what number, right? So the box that I drew times this x and the x plus 1 has to equal this term. That's how this is going to work. So what number goes in, or what thing goes in that box to multiply x to get x squared? Well, the only thing that could go there would be that the box has to equal x. So you see that that's what I put there, and then I multiply. X times x is x squared. X times 1 is, oops, sorry. X times x is x squared, just underline the wrong thing, and x times 1 is 1x. And then I subtract, I bring my value down, the plus 3, and then I do it again. So repeat the process. This is the long division piece, and sometimes we get lucky and we get no remainder, and that's awesome. So then we could go ahead and say that, well, exactly like we did with factoring up above, I could divide those things and get x plus 3. I could divide this by this and get x plus 3. Yay. All right, piece of cake. Now, sometimes there is a remainder, and I did an example of one where you do get a remainder. The process is still the same. If I use this kind of strategy, right, there's two items here. So I come straight up, and notice how the 2x is kind of at the end of that. So that tells you where to place your first value and what to skip. And we went ahead and did all of this, and I got a remainder of -7. So when I showed the division problem at the very end, I showed my solution, the 2x plus 5, and then since my remainder was negative, I used -7, and then my original value on the outside became my denominator like we would have expected. So there's lots of markings there. Let's erase some of the clutter, and we go ahead and we have a nice clean looking answer. This is an example of the result of doing division of a polynomial by another polynomial when a remainder exists. Okay, piece of cake, right? You're going to do a couple of those today. Now, it says jump to last page to remind me to jump to the last page. So let's jump down here to the other kind of division I wanted to review with you, and that's synthetic division. Synthetic division I wrote down kind of as a step-by-step procedure. I have an example problem, is x plus 1 a factor of this big long thing here? And if so, what are the other factors? So first idea, we take our item that we are trying to divide into the polynomial, in this case x plus 1. A key component here is it has to be linear, which means it has to have a degree of 1. So we take this linear polynomial, this x plus 1, we take the plus 1 and we reverse it into negative 1. Right? So we take the negative 1, we put it here, and then we write all of the other coefficients. There's a 1, there's a 3, there's a 3, there's a 4, and there's a 3. So I put those here. If there were ever zeros or there was an x squared term or an x cubed term missing, I would just fill those missing terms in with zeros. We don't have that here, so we just write them all down. The first one comes straight down, so it gets rewritten. That's just part of the norm. And now we go ahead and I tried to do this in blue and purple. We multiply, then add. So I only have a yellow highlighter. So I'm going to multiply these two numbers and put them here. And then I'm going to add these two numbers and put it here. I'm going to multiply these two numbers and put it here. I'm going to add these two numbers and put it here. Here it is again. Multiply these two numbers, add these two numbers. And one more time, that negative 1 in that little kind of corner is used many times. Negative 1 times the negative 3 is, negative 1 times 3 is negative 3. Add them up and you get 0. Look at that. 0 means no remainder, right? Because we have nothing left over. And then we can go ahead and write the new factor using those values we just found and the knowledge that there's no remainder. So we can go ahead and take essentially 1 off of the original polynomial. The original polynomial was x to the 4th. We factored out a linear term, so we have 1 less degree, so now we're going to have x to the 3rd, right? So this thing is now x to the 3rd, 2x squared, x, a 3 is a constant, and my remainder is 0, so I don't really need to write anything for the 0. And you can see how we write this. Now, what do we do next? Well, we might factor more. We might do some more long division. We might do some more synthetic division. This is this idea here. Look at this mess, right? What are we going to do with that 4-term polynomial in there? This is going to lead us into what's called the rational root theorem. It's going to lead us into the next section. But today is only about the division to get to this point in order to move further next time. And in fact, we're not going to be reviewing that at all. If you did need to review any of those things, that's later on in chapter 5. If you're watching this on YouTube, look up rational root theorem, look up Descartes' rule of signs. There's a variety of things you can look up that relate to factoring or breaking this item down. That's not our objective here. So I'm going to go back up. I'm going to grab some pitfalls that I want to mention, a couple special items here. In my algebra book, we introduced the rational root theorem in this section. In the textbook, it's on page 307. Essentially, the rational root theorem is if I divide a polynomial by any other polynomial that has a degree of at least 1, remainder is p, not sub a, p of a, right? So we could take that value, we can go ahead and put that into the polynomial and see what happens. Key kind of item here is that you notice even in this one, you notice how this a is considered to be negative because of the minus sign in front of it. And here this is opposite. So one of the themes we have to keep in mind is that we're going to be dealing with opposites here. Quick application of this, right? Let's imagine there's a question, is x plus 2 a factor of this polynomial? You have a couple different options. You could just do long division. We just did an example like that and hope for the best. You could hope that you get no remainder and quite simply just see if it works. The other option is, right, so here's option number 1. Option number 2 is, let's go ahead and use this remainder theorem and see if I put negative 2 directly into the polynomial, let's just see if we get 0 because it thinks we should. So I'm just going to take the negative 2, right? The negative 2 comes from this, the opposite of that guy. So we take the negative 2 and we put it directly into the polynomial. So my polynomial was this piece up here. I used a calculator to do this, but I just typed this in. It took me less than 30 seconds, and I got negative 220. And what that tells me is that x plus 2 is not a factor, at least not a factor that goes in without a remainder. It is not a factor of the original polynomial. And then I can stop and just, well, stop, because I really only would continue doing long division if it was a factor. This one's not, so I would stop. one more time, this does lead to the rational root theorem, right? There's got to be a faster way to do this. And the faster way is not long division, although long division does work. Long division is really slow, and it gets us into synthetic division. We kind of already went through the synthetic division. Long division takes long. It's a lot of writing. There's a lot of pitfalls. Synthetic division is something that lots of us can do without even a calculator or with minimal calculating. So synthetic division will not only quickly test for a remainder, but if one exists, the other factor is already done, right? Here's the other factor in this problem. So what we tried to evaluate was, does -2 go into that original polynomial evenly? And it turns out it doesn't. So I don't really need this. But if I did want to try to write down some sort of result, I'd write x squared minus 16x plus 83 minus 220 over, and that's where I use this guy, x plus 2, right? So I could go ahead and write down what I get when I divide it, kind of like a long division problem with numbers that doesn't have a nice clean answer, that has some remainders behind it. So it can be done. And I believe that's it. We've gone through the synthetic division. So today you're going to be practicing long division and synthetic division.